Hello, good evening. This is Krishna Kiran, uh, final year student of MSc.Ed Physics from RIE Mysore. Today, we are going to discuss about nanostructures, generally referred to the material systems that are in the range of 1 to 100 nanometers. Specifically, we are dealing about nanowires and nanorods, which comes under one-dimensional nanostructures. And welcome to the exciting world of nanotechnology. Today, we'll be exploring a fascinating class of nanomaterials, especially one-dimensional nanostructures, specifically nanowires and nanorods. And as we delve into their properties, fabrication techniques, and the vast potential applications they hold for future of technology, let's establish a common ground, the nanoscale. It is a realm where materials exhibit unique property due to their incredibly small size. Here, 1 nanometer is our unit of measurement, a billion times smaller than a meter. To visualize this, imagine a hair. It is thousands of times wider than a nanowire. Imagine a human hair shrunk down to thousands of times thinner. That's the basic idea behind one-dimensional nanostructures. These incredible materials come into two main flavors, nanowires and nanorods. Nanowires are typically semiconducting and ultra-thin, while nanorods offer more material flexibility, allowing them to be crafted from various sources. Visualizing these tiny structures can be challenging. Let's consider two different microscopes. One is TEM and SEM. The left side image is SEM image of grown ZNO wires, and the right side image is captured from TEM microscope image of an individual ZNO nanowire grown on AU coated silicon. Let's dwell into the properties of nanowires and nanorods. There are different properties for nanowires and nanorods, namely electronic, mechanical, optical, surface, and additional properties like tunability, biocompatibility, etc. etc. Let's discuss about electronic properties. First thing is high conductivity. This is the efficient charge transport allows from excellent electrical conductivity in certain materials, ideal for miniature transistors and electronic components. The second property is quantum confinement. Electrons and holes are restricted in movement, affected energy levels and influencing conductivity, light emission and bandgap. This enables precise control of electronic behavior. Next comes mechanical properties, high strength to weight ratio. Despite their small size, nanowires and nanorods demonstrate remarkable mechanical strength and flexibility due to fewer defects and high aspect ratio. Next comes the optical properties, light absorption and emission. Quantum confinement allows for absorption and emission of light at specific wavelengths, making them useful in LEDs, lasers, and solar cells. Next, surface properties, high surface area. Then additional properties, namely biocompatibility, tunability. Yeah, now let's come. We delve into realm of quantum mechanics. When material shrinks to a nanoscale, something magical happens. Quantum confinement. In nanowires, electrons and holes, let's think of them as positive charges created by missing electrons, are squeezed into a tiny space, limiting their movement. This confinement has profound effect on their energy levels. Imagine them jumping to different energy states. In a nanowire, these jumps become more prominent, influencing how the nanowire conducts electricity, emits light, and even the range of colors it can absorb. It is nothing but band gap. So, how do we create these wonders of nanotechnology? The very first thing is that the nanowires and nanorods to the real life. The first thing is chemical vapor deposition, namely CVD, is a popular technique. Imagine a chamber where we introduce special chemicals. These chemicals decompose due to heat or other factors, and the resulting material gets deposited onto a surface in a controlled manner, allowing us to create nanowires and nanorods with desired properties and precise structures. Next comes the fabrication techniques as electrospinning. It offers another exciting way to create nanostructures. Imagine a polymer solution, a thick liquid containing long polymer chains. In electrospinning, we apply a high voltage to this solution, forcing it out of a tiny nozzle. As the solution travels through the air, it stretches and dries very quickly, forming ultra-thin nanofibers. These nanofibers can then be processed further to create nanorods with specific properties. Imagine having a mold that can define the shape of your nanostructures. That's the basic concept behind template assisted synthesis. Here we use a predefined template with tiny pores or channels. We then introduce precursor materials, think of them as a building blocks, into these pores. The template guides the growth of the nanowires or nanorods, ensuring they conform to the template shape and size. Once the growth is complete, we can remove the template, leaving behind the desired nanostructures. Now, the one of the main not one of the main applications of nanowires and nanorods, that is electronics. The world of electronics is poised for a transformation with the arrival of nanowires and nanorods. Imagine transistors, the tiny switches that form the backbone of electronic devices built using nanowires. Their unique properties can lead to faster, more efficient transistors, paving the way for advanced processors. Similarly, logic circuits, the complex networks that perform calculations within a computer chip, can benefit from miniaturization and perform improvements using nanowires. But the applications extend beyond traditional electronics. Nanowires and nanorods, with their high surface area, can be crafted into highly sensitive sensors capable of detecting a wide range of physical and chemical signals. This opens doors for innovative applications in healthcare, environmental monitoring, and security. Next comes the nanowires and nanorods for energy applications. The realm of energy generation and storage is another exciting area where nanowires and nanorods are making a mark. Imagine solar cells that can capture sunlight more effectively, leading to a cleaner and more sustainable energy source. Nanowires hold the potential to revolutionize solar cell technology. In the world of batteries, the high surface area of nanowires translates to a significant boost in storage capacity. This means batteries that can hold more charge and recharge faster, powering our portable devices and electric vehicles for longer durations. Furthermore, nanowires can play a crucial role in fuel cells, which generate electricity through chemical reactions by acting as catalysts. They can improve the efficiency of fuel cells, paving the way for a cleaner and more efficient energy future. Yeah. Next comes the biomedical applications. The field of biomedicine is also witnessing exciting advancements with the introduction of nanowires. Imagine delivering life-saving drugs directly to diseased cells, minimizing the impact on health issues. Nanowires hold immense promise in targeted drug delivery, offering a more precise and effective approach to treatment. Beyond drug delivery, nanowires can be integrated into biosensors for early disease detection. These tiny sensors can identify specific biomolecules associated with diseases, enabling earlier intervention and improved patient outcomes. Furthermore, nanowires have the potential to revolutionize neural implants used for treating neurological disorders. By interfacing with the nervous system, they can offer new possibilities for restoring lost functions and improving patients' quality of life. There are few more applications. The potential applications of nanowires and nanorods extend far beyond what we can imagine today. In the vast expanse of space, nanowires can contribute to the development of lightweight, high-strength materials for spaceships and even space habitats. Closer to home, they can play a vital role in desalination technologies, a critical process for converting seawater into fresh water for human consumption and irrigation. The world of textiles is also poised for transformation. Imagine clothing embedded with nanowires that can regulate temperature or even harvest energy from our surroundings. It's a true revolution in wearable technology. These are just a few glimpses into exciting future that nanowires and nanorods promise. There are few more applications left. In the conclusion, our journey into the world of nanowires and nanorods has unveiled a treasure trove of possibilities. These remarkable materials possess unique properties that hold the key to miniaturization, performance enhancement, and the creation of entirely new technologies, from revolutionizing electronics and healthcare to ensuring a cleaner environment and exploring the cosmos. The applications of nanowires and nanorods are truly limitless. As research in this exciting field continues to flourish, we can expect even more groundbreaking discoveries that will shape the future for generations to come. And here is my sincere thanks to everyone. Thank you for joining me on the exploration of one-dimensional nanostructures and the discussion about nanowires and nanorods. Thank you.